Is the screen clear there? Hello. All right. The screen is clear, it's fine. So the questions that we did, I gave you the other day, it was 1 and 2. So the first one, in a region can be described by E. So that E is a vector. The E is a vector, which means it has a component in the X, in the Y, in the Z direction. So E is a vector, not a scalar, it's a vector. The electric field E is a vector, having components in the X, Y, and Z, like what we were doing yesterday in classical mechanics. So those are the components of X, Y, and Z. Estimate the charge density in this region. So it's a matter of formulas. Whenever you're given electric field, you want the charge density in that region. So it's a matter of just playing around with the formula. So the electric field is given by E, which is X composed 6X in the I direction plus 2Y in the Z, in the X in the Y direction plus 2Z in the K direction, which is the Z axis. So estimate the charge density, we use the Gauss law in differential form, grad. So we are estimating the charge density. So that charge density is represented by that rho, the charge density, that rho at P, which is there. So grad E is equals to P over that epsilon naught. So this symbol, it's a constant. It's not an E. Those E are different. So the E, which is having a vector, the E, which is having a vector, and the different in such a way that that one you write it as epsilon. You are doing maths, epsilon naught. So this E, they are different for the one for electric field and the epsilon naught, which is a constant. Okay. So we compute the divergence of E. Why are we computing the divergence of E? Because we are looking for grad dot E, which means for us to find the charge density, we need to calculate first using Gauss law differential form of grad dot E. So that dot is a dot product. Hello?
Oh, no, I not see. I'm just...
Okay. So we differentiate partial derivative. So this grad, you do the same like what it means in the classical mechanics, like what we've been doing. Grad, it means partial derivative, partial in the I, dot. So which means whenever you see this symbol, what comes in your mind?
Partial derivative.
Yes, partial derivative, partial x, but not just partial x, then there is an I. Then plus the partial with respect to what? Y.
Y.
Then in the J direction.
J.
Then the last one we do partial derivative.
Z. Partial Z.
Yes, in the what?
In the K.
Yes, so that is the meaning of grad. So that already E is having components, like what we were saying yesterday. So which means when you dot those two, which means you are putting a dot here, bracket. So that one was 6x in the I direction. And then the other one, we are talking of E, then 2y and 2z in the. All right, so it will be plus 2y in the J direction, and then plus 2z in the K direction. Then you close your bracket. So this is what we are referring to as dot product, which means you will be multiplying, we'll be dotting this in dot product. So dot of grad E. So you find out that when you say the first component with the first component, it's going to give you partial of 6x. And then I dot I, what did we say yesterday? I
1
dot I is give you 1. That's excellent. I dot I give you 1. And when you find I dot K, it's 0. J dot K, if they are not the same, then you know it's giving you 0. It's only give you 1 when it's what? When they are the same component. And when you do dot product, you are going to get a scalar. It means now it's a number, it's no longer a vector. Whenever you see a dot product, the result is a scalar, not a vector. It will be a number. So you do the first component, you multiply them together, you are going to get partial of 6x. Partial x of 6x. Then you go partial y of what? 2y. Plus partial z of 2z. So in other words, you are differentiating that function with respect to x. You keep the other ones constant. So you are going to get 6 plus 2 plus 2, which means 2z with respect to z is 2. If you differentiate this with respect to y, 2y with respect to y, you get 2. Any question there?
No.
So 2 plus 2 plus 2, 6 plus 2 plus 2 is 10. So that is only grad dot E. So we got 10. So now we use the concept that since we know our formula, remember the charge density, I told you it's given by the symbol rho, which you are looking for. This charge density is given by the symbol rho. That rho is the charge density. Remember, that is what we are looking for here. Estimate the charge what? Density in the region. So in other words, find this P, which is not a straight P, it's like a bent like this P, which is rho. That is the charge density. So our formula, which we started with, was E grad dot E is equals to P over epsilon naught. So if you want to make P subject of the formula, what are you going to do here? If you want to make P subject of the formula, so P remains where it is, then I'm going to multiply both sides by what? By epsilon naught.
Changing.
Yes. So it's going to be a grad E.
Right.
Grad dot E multiplied by epsilon naught. That's what you do, so that you make P subject formula. Since you are looking for this charge density alone. So once we do the dot product, we are done. We found the dot product is 10. So 10 times epsilon naught, that is your charge density. That was the first part. So any question there?
Is the epsilon not having a value?
Epsilon naught, it's a constant. It has a value, it depends. It depends. Some with the constant that will be given, but epsilon naught is a constant. There's a value. But if you leave your answer like this, you are also correct. You are also correct. The charge density, yes. So which means if you just know the epsilon naught, which means you just multiply it by 10, and then the units will be coulombs per cubic meter, the charge density. Coulombs per
Okay.
Okay. Yes.
All right.
Maybe if we go up, yeah, and that when we were doing the dot product, you said,
Yes.
multiply the partial. You say it's partial over partial x, multiplied by the 6x.
6x, yes, multiplied by I times I. You are multiplying the first component by the first component, plus the second component times the second component, plus the third component times the third component. Always like that.
Okay, so the partial partial over partial x multiplied by 6x, it gives you the partial 6x over 6x, this one.
Yes, that is it. That's correct.
Oh, all right.
I times I is what?
It's 1, I know.
That's why we did not include the 1, because we know already when you multiply any number times 1, it remains 1.
It's the same, yeah.
The I times I give you 1. So partial of 6x, they are differentiating with respect to x, then that's the answer is just 6.
Oh, I get it.
So that was the first part. So now we are going to the second part, which is what a conservative field. So this is the theoretical part, and something previously in metric we were referring to a conservation force, whatever. So this is just a theoretical question which needs you to revise your theory in terms of conservation. All right, but when you are conserving, you are preserving something, there is no loss. So let's see. What is a conservative field? Which means a conservative field is a vector field where the line integral. What do we mean by line integral? The line integral. The line integral between the line integral, or it can be a line integral. The line integral between any 2 points. These are the 2 points which I have put. Any 2 points is independent of path taken, which means path does not affect, so it's independent of path. Whether the path is rough or the path is smooth, when we're dealing with the conservative force. So when it's independent of path, then you know it's conservative force. But when it's dependent of path, then it's non-conservative field. So here it's a conservative field because it's independent. They go hand in hand together. When it's conservative field, is a vector field where the line integral between any 2 points is independent of the path. The path which you are going to take from A to B. So this will be our path. From A to B. The path. Suppose it's A to B or B to C. So that is the path. It's independent. In other words, for a conservative field, what are we talking about? For some scalar potential, remember potential we referred with V, potential, for example, potential energy. The divergence, here we're dealing with the dot. The dot give us the divergence of E. Can you see where it's written? The divergence. Something diverging. It's not converging, it's diverging, moving away. It's divergence, moving away. Convergence, we are referring of something coming into the arrows. For example, when we talk of divergence, if I'm to put a point charge, so there is divergence away from the point. Can you see the divergence moving away from a given point? When you talk of convergence, the arrows, they are into that point. They are converging. It means they are coming to one certain point. That is the difference between divergence, the arrows away from that point. So the divergence, you calculate it by the dot, dotting the energy, the electric field E, which means grad dot the electric field E, you get the divergence of that electric field. But for the when they are referring to for the curl, it means that when you cross grad and the electric field, if you are using the cross product, not the dot product, the cross product, you are going to get 0, which means the curl is 0. So that is the curl, the difference between the curl and the divergence. For curl, we are talking of cross product equals to 0, and the divergence, for the divergence, we are talking about dot product. So such fields such fields have network around any closed path. Conservative electric fields usually arise from static charge distributions and are irrotational. So these are some of the static charge, which means electricity. If a path is closed, means no network along that path. So these are some of the theoretical. It depends also on the textbook that you are using. You find out you can add other information, only this one, where you can also get some additional information on what is a conservative force. But this is the summary when they refer to a conservative force. I mean a conservative field, not force, sorry. Then for question number 2, consider a system of circular loop placed at a distance r from a long straight current carrying wire, which is in the plane of the loop. If the separation r is much larger than the radius of the loop, derive an expression for the mutual inductance of the system. Then the next question was estimate the mutual inductance of the above system if r is 1 meter and the loop is radius 1 centimeter. The method of just substituting values. What would be the mutual inductance if the straight wire is perpendicular to the plane of the loop? So let's derive first the first part for the first, which is question number 2. So we are deriving the mutual inductance where the radius r is greater than. So r is greater than a. Where are we getting that? We are getting it. Consider a system of a circular loop placed at a distance r along the straight current carrying wire, which is in the plane of the loop. If the separation r is much larger than the radius of the loop, So that's where we are getting the indication. It's much larger than the radius of the loop. So R is the separation, which is much larger than the radius of the loop, which is our A. So that's where, by saying much larger, which means we are indicating those two greater than, which means more
So A stands for the radius.
of the loop,
Mm.
which is A. R and the loop radius. Okay.
Okay.
So let's continue with the problem. Let's continue with the problem. So what we are confirming is A is B, the radius of the loop, isn't it?
Okay.
And then R distance from the loop to the wire. The distance from the loop to the wire. And I be the current in the long wire. So when you are deriving, I've shown you where this is coming from. Why? It's much larger. That's how you represent in terms of those symbols, greater than, less than, much larger, you write it like that. So when you're deriving, let I, so that we know your symbols, what I is representing. So I will be representing the current in the long wire. R is the distance or the separation from the loop to the what? To the wire. So R is representing the separation. A is the radius of the loop. Then the magnetic field, D. Electric field, you know, is represented by E, isn't it?
Mm.
Of electric field, E. Then magnetic field is represented by this symbol B. So U naught multiplied by I R from the wire at distance R. So that is our magnetic flux, the formula which we are going to be using calculating magnetic flux. Then through the loop, flux is given by the symbol, that phi. We call it the symbol phi. This one, it's phi. So that phi is representing D, which is the magnetic field, multiplied by the area. So the magnetic field multiplied by the area. The area, pi r squared, area of a circle. What is area of a circle? What is area of a circle?
Times the pi r squared.
Yes, pi r squared. So our loop, a loop, something circular, isn't it? So if you want the area, A is the area. So that loop is like that, which is the area of that loop. But this loop is having a radius. What is the radius of that loop?
It's A.
It's A. So our R, instead of putting R, we are going to put what? A. So this is our A. So where it says area, we are replacing with pi r squared. So pi r squared. R is A squared. That's where we introduce the A. Already the formula from a magnetic field, it was given. You must know that one. So if I say magnetic field, this is my magnetic field multiplied by the area of the loop. There are things that are going to cancel, isn't it? The pi, can you see? Yes. The pi on the denominator cancel with the pi that one. So pi disappears. Okay. And then to this equation, I'm just going to add multiplying by a squared, that will be left out. So this is the a squared, this is the a squared. So that is our symbol for flux, which is the magnetic field multiplied by the area.
Area.
Yes, area of the loop. So now, once we have our formula for magnetic flux, we can, by definition, the mutual inductance is the same as Mi. What is Mi? Where M, what is our M in our case? And what is I in our case? So check now. From the above equation, we found that the flux is equals to what having there on the numerator is this is our flux. This is our flux. So if I want to find the mutual inductance, we are going to say the mutual inductance from the equation of the flux. What is left out, which is the M, this was the current. I just removed the current from this formula, which is here. From the flux, I just separated, I removed that I, which is the current. The I, which is here, current in the Y. When you remove it from there, in other words, you are going to be having, saying from that equation, it can be you can rewrite the same equation by saying this is the flux, which is still the same equation. So you can rewrite it like this. You have to say the flux. You can also write it like this. To say U naught over 2R, which is our radius then, multiplied by A squared. Everything, you are multiplying it by I. I just separated it so that the I stands alone. Can you see? I just removed the I from the whole equation. Why am I doing it? So that you know that this flux, you can also write the definition of mutual inductance, which is M times I. M times I. So in other words, that flux can also be written as mutual inductance times the current, like this. So from here, you can clearly see what is M is equals to. M will be equals to.
It's just the flux over I.
So this will be M. Okay. So that's what I was trying to show you, where this M is coming from. So that's M is coming from there. With the I. Okay. So that is the mutual. Yes, they only want the mutual inductance. The question was asking the formula for the mutual inductance. So now we have our mutual inductance, which we have derived. This is what the question was telling us. Derive the formula for the mutual inductance. So we have derived the formula for the mutual inductance. M, which is referring to the mutual inductance, is U naught A squared over 2R. So the next question now is number B. We are done deriving. Now we are going to number B. B is saying what? For B, saying estimate the mutual inductance of the above system. You already derived the formula. You were not given the formula. So you have derived the formula. So now you want to estimate. What are you given? You are given the value of if the radius is 1 meter and the loop radius
A 1 centimeter.
the loop radius is 1 centimeter. So that's what we are now doing now. We substitute the values, put them back on the above formula. That's what we are just simply doing. So the R is 1 and the A is 1. A is not just 1, but it's 1 centimeter. And you convert that 1 centimeter. How do you convert 1 centimeter to 1
Divide by 100.
Divide by 100? So it's just the same as times 10 to the power minus 2 meters. 1 centimeter is equal 1 times 10 to the power minus 2. Or as a decimal, you can write 2 zeros,
0.
then 0.01 meters. Just so now it's a matter of substituting. U naught, it's a constant, just like epsilon naught, it has a value. So that U naught, it's a constant, it has a value.
We are not given those values.
Values are given in an exam, you'll be given. These ones are given. Values you don't memorize, especially epsilon naught, you don't have to memorize them. Given. U naught, you don't memorize, you are given. But A squared, you convert to meters. So the radius of the loop, you square it. 2R, the distance of separation was R. That's all. Then it's a matter of plugging in everything. And when you are done, put your units. This is what? H represents what? The mutual inductance H. What does H represent? The first time? Henry.
Huh?
You've never heard of Henry's?
Of
Henry's.
mm,
The first
No.
time to hear that. All right. For inductance.
electrical.
Hello?
I was saying it's an electrical inductance
Yes.
unit.
So H Henry. So I'm trying to show you the H so that you can see it. So Henry is a derived unit in the International System of Units, which means SI, International System of Units, used to measure what?
Inductance.
Inductance. That's why I'm showing. So that's H. So that when I say it, you know that the H is the Henry's. So that's what we mean by H. That is the symbol for inductance. But in this case, it's mutual inductance. So I've shown you how they separated the flux. How can you convert it? Instead of flux, it can be also mutual inductance times current, or flux can also be the magnetic field. Magnetic field B multiplied by the area, you get the flux. So it's a matter of manipulating the equations. That's what happened there. So let's move on. Now you answer, you put it in Henry's. In Henry's, H, capital letter H, not small letter. Any question there?
It makes sense.
Yes, you're just substituting into M. And the last one, if the wire is perpendicular to the plane of the loop. Right, so let's go to the question. The question, what would be the mutual inductance if the straight wire is perpendicular to the plane of the loop? So that's what we are doing. We want to calculate the mutual inductance. If the straight wire is perpendicular, which means it's at 90 degrees to the plane of the loop. So let's go about it. We solve that one, which is the last one, C. If the wire is perpendicular to the loop, in this configuration, the magnetic field lines are symmetric around the wire and do not pass through the loop, since the field circles around the wire and is in the plane of the loop. So the net flux is equals to 0, which means like what we say, the mutual inductance. Whenever you talk of mutual inductance, you involve the formula for flux, which is flux is equals to the M times I. So we always refer to flux. So the net flux is equals to 0. So if this is equals to 0, if this is equals to 0, what can you conclude? Already you have been told that I, what was I? I is already having a value, isn't it?
Mm.
I was already having a value. What did we find? What was I given?
Mm.
I
Mm.
is already having a value because we have been told that consider as a system of a circular loop placed at a distance R from a long straight current carrying wire, which means this wire is already carrying what? Current, isn't it?
Mm.
Yes.
Mm.
So it means I cannot be what? I cannot be 0 because the wire is carrying what? Current. Although
Right.
we don't know how much current is it carrying, but we know that it's not 0, isn't it?
Mm.
So if I am to give you this equation, M0 is equals to M times I. Which one are you going to equate to 0? Is it I or it's M? Already you have been given that the net flux is going to be equal to 0 if it's perpendicular. If it's perpendicular, you already know that the net flux is equals to 0. So if the left-hand side is 0, where there's the flux, I put the 0. This is the flux. I put the 0. So 0 is equals to mutual inductance times the current. But we know that current is not 0. So definitely what could be 0?
Mm.
M.
Definitely.
I want to multiply numbers M times I, and I must get a 0. Which one between M and I should be 0? Is it I or it's M?
It's
It has to be M because current is not 0, isn't it? Current, so it's going to be 0 times something. That's how I'm going to get 0 here. Current, we've been told it's already carrying some current, although we don't know how much, but it's there. So which means if I'm going to get a net flux of 0, that can only happen if M is 0 at perpendicular. So which means that's why we arrived at this answer, to say M is equals to 0, so that we can get a net flux of 0 because of the perpendicular. Okay. The wire is perpendicular to the plane, so which means the flux, the net flux is 0. Whenever they tell you this, you know the net flux is 0 if the wire is perpendicular to the. So in other words, 0 is equals to the M times the I. But we know it's the wire is already carrying current, so which means 0 times I. So the mutual inductance there is going to be 0. In other words, it implies that M is equals to 0. Because what number are you going to multiply by current to get 0? It's just M, which is 0. Any questions which you want to add, subtract? It's already time. Where do you want to understand? Where do you want to need clarity?
Okay, maybe on the last question. Why is the net flux 0?
Because the wire is perpendicular to the plane. That is
Okay.
that statement already you know that if the wire is perpendicular to the plane, the net flux is 0. That's why where there is 5, we are putting 0. Okay. All right. So if there's no any other questions, we may stop here. So we'll meet next week. You said what is the time?
What?
What time are we meeting for electricity and magnetism? Date, you said what? It's Tuesday and Thursday.
Yeah, Tuesday and Thursdays.
It's fine.
It's gonna be at 5, ne? Or 5:30.
Tuesdays and Thursdays are first 5.
All right.
Okay. We'll stop here for that.
Thank you.